Ever wondered how AI can understand a complex story, translate languages, or even predict the next word you type? It's mind blowing, right? But here's a secret. At its core, the most powerful AI architecture today, the transformer, has fundamental blind spot. It can't tell the difference between dog bites man and man bites dog. It sees them as exact same words, just jumbled. That's a huge problem, and the solution is called positional embedding. The transformer uses something incredible called self-attention. It looks at all words in a sentence simultaneously to understand their relationship. Think of it as like a giant brainstorming session where everyone shouts their ideas at once. Super efficient. But here's the catch. Because it processes everything at once, it loses the sequential order. It can tell dog and man are both present, but not who did what to whom. This is called permutation invariance, and our AI needs to know its sequence A, B, C's. Here is the simple solution to this problem. Why not add just a number to each word? Word 1, word 2, word 3. Sounds simple, right? This is integer based positional encoding. We could add 1 to the first word embedding, 2 to the second, and so on. But this has a big problem. What if your sentence has 1000 words? The number 1000 is much larger than 1, so the model might mistakenly think that the word at position 1000 is drastically more important than the word at position 1. It introduces an artificial bias in magnitude, making it hard for the model to generalize to varying sequential lengths. Our AI needs a smarter numbering system. This is where the brilliant idea of using sine and cosine functions comes in. Instead of simple numbers, we use patterns. Imagine a unique musical note assigned to each position. Sine and cosine always produce values between -1 and +1. So position 1000 won't accidentally seem bigger or more important than position 1. Every position gets a unique combination of sine and cosine values. It's like a unique fingerprint for each spot in the sequence. The magic is values for nearby positions like position 5 and 6 will be similar, while values for a far apart positions like 5 and 50 will be very different. This helps the model understand not just absolute position but also the relative position, how far apart two words are. It's like knowing exact street number, but also that house number 5 is closer to 10 than to 100. Here is how the formula looks like. We have an equation for sine and the other for cosine. Here the position means that's the word position first, second, third, fourth. I refers to different dimensions within the embedding vector. Each dimension gets a different frequency. This 10,000 parts simply create different spread out frequencies for our sine and cosine waves. This allows the model to learn to attend different wavelengths of positional information. D model is the size of your input embedding. So for each word, we calculate a positional embedding vector. This vector has the exact same size as our word embedding. Then we just add them together. This simple addition injects the positional information directly into the word's meaning, letting the transformer know not just what the word is, but also where it is. Let's start with this example. We have a sentence, the dog bites the man. The embeddings are assumed to have a size of 6. So all these tokens can be represented in a vector size of 6. Let's calculate the position encoding for the word at the position 0, that is the. First we will put I equals to 0. When we put position equal to 0 in the formula, the numerator becomes 0, due to which the whole terms become 0. And sine 0 is 0 and cos 0 is 1. So changing the value of I does not matter. Even for I equals to 1, the values will repeat 0 and 1. Now we get the values for position 2 and 3 for the position embedding vector. Since position is 0, this whole vector will be alternate zeros and ones. Let's compute the position embedding vector for the second token, that is dog. At I equals to 0, the denominator is 10,000 raised to the power 0 by 6, which makes it 1. So sine 1 equals to 0.84. Similarly, we will calculate the further cos and it is 0.54. So these are the first two values for the position embedding vector. Let's calculate the next two. Increasing the value of I to 1, the denominator is now 10,000 raised to the power 2 by 6. So the sine value will be 0.04 and the cos value will be 0.99. Let's change the I to 2 and then put the values in the formula. Now we get 0.004 for sine and 0.99 for cos. So here are the final position embedding vectors for the first two tokens, the and dog. Now look, position 1 and position 2 have two different numbers, but they share the same underlying mathematical structure. This difference is what tells the transformer, I am right after you. When you calculate this for the whole sentence, you get this beautiful heat map. See how the colors change vertically down each dimension, giving every word a unique barcode. If we increase the number of tokens and the embedding dimensions, here is the result. With 100 tokens and a dimension of 128. Notice how the pattern is cyclic and continuous, meaning the model can easily infer the relationship between any two words, no matter how far apart they are. This position encoding vector is then added to the actual word embedding, and the result is then fed to the transformer. This powerful addition is what allows the transformer to truly understand context and relationship within the sequences, allowing their amazing capabilities in NLP and even in computer vision with a vision transformer. If you want to dive deeper into how this model can learn language, how they apply to images, or just stay updated to the latest AI breakthroughs, make sure to like this video, subscribe to the channel, and hit the notification bell. What other AI concepts blow your mind? Let me know in the comments below. Thank you for watching. See you in the next video.